Let's continue on with our discussion on the formula representing the spin-orbit interaction. So these are the key points that I point out before the break. It is the orbital motion, that is to say orbital angular momentum, that gives rise to a B field. We don't need to buy a magnet. That's why we also call it the internal B field. And the electron spins is associated with a magnetic dipole moment due to spin, the subscript S. The interaction energy from classical E&M is minus mu dot B, and therefore there will be a term like that. And this particular term that should be added to the Schrödinger equation or the Hamiltonian. This part you solved last term, and now we have a new term. Therefore, we have a new Hamiltonian, and the question becomes, what does this term do to the eigenvalues? And that will be a part of the fine structure. So that is the big picture. To get a sense of how big this internal field is, this orbital motion gives rise to an internal field. We can easily use classical EM, even Bohr model stuff to think about it. So the electron is in an orbit, say this picture. Then Biot-Savart law says there is a B field that goes like 1/2r, the orbit radius, mu over 2r, and how big is the current. So a charge moving around, current means you sit at a point per second, how many charge goes through that point. That is a current. So that is related to how fast the electron moves, and how many times means how per second, the velocity, the speed, and then divided by the circumference. It is how much time the charge passes through one point. So there's a charge minus E. So this will be the current. Now, with the V here, we multiply a mass divided by a mass that's nothing, okay? We multiply an R divided by another R, there's nothing, but we have this combination being the angular momentum. That is R cross P, okay, RP. They are perpendicular, so you don't need to do the cross product. So this is the angular momentum. So therefore, without much effort, we have a relationship. The internal field, through the Biot-Savart law, there's an addition factor of R. So you have R squared here, you have an addition R here. It turns out that the magnetic field, due to orbital effect, is 1/r cubed with some constants. That means we can estimate how big this field is. You just pick any state you want. 2p is natural because L equals 0, you shouldn't have any orbital angular momentum. L is 0, okay? So you pick a 2p state, you pick the wave function, you have to estimate what is 1/r cubed. In fact, for hydrogen atom, this expectation value can be carried out, well, rather tedious, but it can be done. And we found that at the end, all in all, this B field is about 1 tester. So it's pretty big. At least it's not small. We are not talking about Gauss, the Earth's magnetic field, that kind of thing. It is 10,000 times of that. So even without an external magnet, this p space orbital motion could lead to something like 1 Tesla's magnetic field. So it's not small. We should take this into account. That's the story. Okay. And I mentioned that for this 1/r cube, the expectation value of hydrogen state. So you take a hydrogen state, left side, right-hand side, do the integration. It turns out that can be done, but the result is rather tedious, and we are using this one. Okay, so here, this page has some result. And this week's sample questions also invoked these integrals. Now we come to the meat of this part. The first thing I would like to do here is to find a full expression for this spin-orbit interaction term. For the reason that some of you may be doing some project later on more modern solid-state physics, condensed matter physics, or cold atom physics, you really need this term very often in your work. So I will try to give you different forms of the same effect, because in atomic physics, if you do cold atom, cold molecules in Professor Wang Dajun's lab, that will be one form. The atomic physicists use this form for spin-orbit interaction. But if you do condensed matter physics, topological insulator, things like that, then you see another form. Then when you do a band structure calculation, traditional solid-state physics, you see another form. Okay, but the physics is the same. But at the outset, I would like to declare that whatever we do here, it is just a derivation based largely on classical physics. But spin is relativistic quantum mechanics product. It comes from the Dirac equation. Therefore, a complete derivation should start from the Dirac equation, which is relativistic quantum mechanics, and then you will get not only the spin-orbit interaction term, but other relativistic correction term in one shot. So what we are doing here is try to make this classically physical transparent, meaning it's easier to think about what it is. So let's start our derivation. This first picture is important, so pay attention. I'm trying to depict the orbital motion of an electron. Charge minus E, so there's a minus sign attached to the charge, minus E. And it is the electron's motion that I'm drawing here with the vector V. This is a vector V, meaning there's a magnitude V, there's the direction as shown in the arrow. And generally, the nucleus has plus ZE. Hydrogen will be plus E, okay? But for other heavier thing, it may be plus ZE, where Z is the atomic number. With this, we have the electron in motion. Therefore, we can multiply a mass of electron, mv becomes the momentum. Okay? And now it is at a position depicted by this position vector R. Again, there's a direction, okay? So from the nucleus to the electron, so pointing that way, so there's a vector, okay? And with this picture, R cross mv will be the angular momentum. And we want that to appear at the end, okay? So this is the point. Now, we know that the electron is moving under the influence of an electric field due to the nucleus. So there is an electric field, right? And the electric field is given by, due to the nucleus Coulomb's law, basically. So charge divided by R square. And since this charge is positive at the nucleus, it's radially pointing outward. This is the field, electric field. So it has a direction. Okay, so up to here, so far so good, I hope, right? And now, the electron will sense a force. Why we are considering the force? Because we want energy. We want an energy in quantum mechanics to add that term in, okay? We don't like force. So we write down the force and write it into an energy, potential, something like that, okay? So now, we have a force minus the electron charge times the field. That's fine. And for this field, we can write it as a potential energy function with a gradient of it. Okay? So this minus sign actually comes with this force. Okay? Force is minus gradient potential energy. It is not the potential, it is the potential energy. The potential goes with the field. This is the force, so this is potential energy. Okay? And this is true for this thing being conservative, that will give a conservative force. And this line is true for conservative force. And if it so happens that this is central force, meaning the field goes radially outward or inward, then it is central force. We have this V not being X, Y, Z or R theta phi, and only R only. And this gradient can be taken easily, and that will be just a derivative of the radial distance dVr dr. This second line requires central force. Okay? Now I'm so careful here, again, due to the fact that nowadays you will use spin-orbit interaction in many different areas. So later on, in some formula, I will write this form, meaning I may not need central force in that equation, in that form of the spin-orbit interaction. Then when I write, when you see something like this, we need a central force to create this V of R, okay? So there are slight difference in the forms at the end. Behind, there are some assumptions that you should be aware of. So let's continue. And this page will be the key, this and the next page, okay? The question becomes, so far we are only talking about E field, but we have been discussing that the orbital motion will lead to a magnetic field. So how can we get a magnetic field at the position of the electron so that that can interact with the spin, magnetic dipole moment, okay? So that is to say, the question becomes, how does the B internal relate to the quantity we introduced so far? The electrons is moving with momentum P, angular momentum L, there's a E field acting on it, and there is a force represented by minus gradient V, okay? So now we jump to the frame of the electron. So I repeat the picture on the last page just to remind you of the two vectors, V with direction and the R also with direction. So now, if you sit on the electron, when the electron itself, as seen by the nucleus, is moving this way, counterclockwise. You see my cross, okay? So now if you sit on the electron viewpoint, the nucleus will be moving this way. Okay? So if I take this viewpoint, this ring will be minus V, at least at this particular moment. I'm referring to this particular moment so that when I sit here, what do I see? Okay. And similarly, this R, if it is pointing from the proton or from the nucleus to the electron, it is still this R. See the arrow pointing into the electron because it's the same vector. Okay. Now, if you take this viewpoint, then we can use E&M now. The current density due to the motion of the nucleus will be the charge times the velocity. So it's just ZE multiplied into minus V, so you have this. Then the B field by Sheffield law, your Griffin's book, I look it up, it's chapter 5, okay? So there is a formula to give the B field due to a current density. And this is J cross into R, and it is this R. Cross into the position that you want to find the B field, okay? So if you plug this J, I mean this one, into here, okay, you will get this formula. That is the B field that the electron feels. And you pick up a cross product from this Biot-Sheffield law, and therefore you pick up V cross R with a minus sign due to this minus V. Okay. And a cross product with a minus sign, you could flip the cross product. So you have R cross V picking up. And R cross V is R cross P divided by the mass. Therefore, you already pick up the angular momentum. So our story is okay. The orbital motion will lead to a B field at the position of the electron itself. Okay, so that is the formula proving our story. Now let's move on. So I will pick this line and move on. So I copy that line through. The internal B field goes like that. Now I even know the prefactor. You started to see 1 over R cubed. That is what we got, hand waving in that page. Okay, so everything is really there. It's really there. Okay, now I multiply an epsilon 0 divided by an epsilon 0, so nothing. This is 1, but I want to write it that way because at the beginning, we are saying that it is actually an electric field that the nucleus is applying on the electron. So we want to express it back and see how this E field is related to the B field that we are talking about. That's the point. So after we do this, this dash part, okay, is exactly the E field that we wrote down. Okay, you should have an R square, fine, but I have an R. So if it is R square, it will be a unit vector R that is exactly that form, okay? So this dash thing happens to be the E field, okay? And I think you know, 1 over square root epsilon 0 mu 0 is speed of light c. So this factor up there will give us 1 over c squared. Okay, so now for those who know electrodynamics up to the special relativity part, I think that will not be very unfamiliar to you, okay? So actually that is also a transformation as well. So all in all now, what we've already seen is that when the electron is moving under the influence of the nucleus, there is a B field that is felt by the electron, given by E cross B, okay? So if you don't like all this complicated E and M, okay, you just want to learn quantum mechanics and the effect, fine. I summarize it in the box here, okay? You must appreciate what the formula says, even if you don't like the proof, the steps. So here I will let the formula speak to you directly. So I wrote the formula down again, but let's read this formula out in order. 1, 2, 3. Okay, so let me read it out for you. This formula says, when an electron moves in, that is V. Okay, that is the electron's velocities to start with. When the electrons move in, an electric field due to the nucleus, then it gives a magnetic field acting on the electron itself. That is the content of this formula 14. Okay, that is the more important thing among all these lines of mathematics. Okay, basically you can also sense that in the previous Hamiltonian last term you saw for the hydrogen atom, you just write down kind of like the electrostatic interaction, the Coulomb. You write down the Coulomb energy, okay? But you haven't taken into account that the electron could move. And that's why when we take into account that it can move, there will be an additional term called spin-orbit interaction. And that is another way to look at the story. And that part of the story is related to this equation 14. It says, the electron's motion, but now it's not moving in free space. It is moving in an electric field due to the nucleus, or due to something else actually at the end, that it also sends a B field. That's the whole story, okay? In solids, it may not be due to one nucleus, it will due to an array of nuclei, because in a solid you have a dense array in regular positions, okay, the nucleus says. So, but all those, they also contribute a E field in which the electron is moving. Therefore, this effect will also be there. That's the point. So with this, we are done, okay? We are done and we are embarrassingly done. We will see, okay? Now, I picked the last line. B, 1 over C squared E cross B. Again, physicists like to multiply it 1, subtract, add 0, things like that. So here, again, I multiply a 1. So minus E, minus E. This is the force, okay? And the force will be minus gradient V. The minus sign cancel out the minus sign down here, okay? So therefore, I pick up gradient V, okay? And then I do another 1, multiply another 1, M divided by M, nothing, okay? So now I have gradient V cross into the momentum of the electron. So I find one form that you will see very often in solid state physics when people discuss spin orbit interaction. You will see a term like gradient V cross P. So this is why it is there, okay? And the prefactor becomes something like that. Everything is still fine. I have been multiplying 1 into it. And up to this point, this need not be central force. As I said, in a solid, you have a dense array. The nuclei form a square lattice, for example, a simple cubic, and any position there, you can hardly find something that is central, right? Because the contributions come to many different nuclei. Nonetheless, up to this formula is still okay. Now, if I write this, then behind the scene, maybe I'm thinking about one atom. From the nucleus, I have this central force. The E field is radially outward, so I have dV dr. Okay? And then if I now represent R cross P being the angular momentum, then finally I have to form very useful in atomic physics. Okay? So all in all, the summary, B could go like gradient V cross P more generally, and then it can be written into a dV dr. Now there you pick up a derivative, okay? So if this is a constant, doesn't work, okay? Even there's a potential, doesn't work, okay? And also you need a gradient going in the radial direction, and then you have the field, the magnetic field proportional to the orbital angular momentum. Okay, so that back up our story. After a few pages, we succeeded in finding the prefactor. We argue that the B internal is proportional to L, but now we have this chunk of thing in front, okay? So this factor, some constants, no fun, but this kind of thing will determine the strength. So you can look at different situations and you can find out, you realize that this particular case will have a stronger internal field, therefore will be stronger spin-orbit interaction. Finally, we need the interaction energy, but that's easy because this field B will interact with the spin magnetic dipole moment mu s. And we know that through Stern-Gerlach experiment, the magnetic dipole moment due to spin is minus E over ms. So we just copy this thing and dot it into the B that we found. And that will be an interaction energy. Now in quantum mechanics, we need to find energy so that to add to the Hamiltonian. Hamiltonian is an energy. So therefore, we put this thing dot into the B on the last page. For atomic physics, we usually write it in this form. Therefore, you see the S dot L. And you know what is happening in front. Okay? And if you plug in the Coulomb thing, okay, 1 over R, then you will find another 1 over R squared that will give you the 1 over R cube that we saw previously. Okay? So this is the end of the story. We have found it, done. Okay, within our argument. We make use of E and M and things like that, okay? And interaction term, a lot of things. For our purpose, later discussion, I would like you to take a look at this combination. So it's 1 over R dV dr. In the context of an atom, it is very useful. And all in all, that means this interaction term depends on the orbital angular momentum, therefore theta phi part of the spatial wave function. And this is the spin of the electron that has nothing to do with space. But there is an R theta phi, right? X, Y, Z, so R theta phi. The R remains in the prefactor. So the prefactor, the simplest thing to remember is it is a function of R. Okay? But I say embarrassingly done in the following sense. If you start with the Dirac equation and do everything correctly, there is a factor of 2 down here. And that equation 15 is the precise formula for spin-orbit interaction. I will not work out the factor half for you because that will take quite a long discussion. There are 2 ways to do it. Way number 1 is to do the transformation back more carefully. Because we are doing rotating frame, it is accelerating frame. So even if you do special relativity, that transformation should be done more carefully. If you want to read how this is done, there is an undergraduate book by Resnick, that is the Halliday-Resnick's Resnick, Espert and Resnick Quantum Physics. There's an appendix in which the author worked back this half for you, okay? But actually that was much effort. Another way is to spend 4 hours or so to understand what the Dirac equation is about, and then from there work out how an electron moves in an external field, and then suddenly you will see the spin-orbit interaction term in complete form. Because after all, spin is relativistic effect, and the proper way to do it is start with relativistic quantum equation, which is the Dirac equation for an electron. Okay? So for us, don't worry, I have done 80% or 90%. I am off by a factor of 2. I don't feel that bad myself. I hope that you won't feel that bad, because after all, the real physics has to do with how to handle this part as a perturbation. Okay? So that is the end of the formula. For the rest of this part, I've tried to rewrite this formula so that some of you later on doing atomic physics, you know, this form is spin orbit. Some of you do solid state physics, this form is also spin orbit interaction. They're the same thing. So this is the set of different ways to write the same thing, okay? So what I'm saying is that the B field, as discussed, can be written in this or in that, okay? You see different ways. And also, remember the S, the spin angular momentum, can be expressed in terms of the Pauli matrix. Okay? Just off by h bar over 2, I think, right? Okay? So it's h bar over 2 sigma. So with this, you will see several different forms. So form number 1, I take this, the constant, okay? And then I have the B field being grad V cross P, okay? I'm using this, okay? And then I will dot it into the magnetic dipole moment that is expressed as minus S with a factor, okay? So this is a very standard form for spin-orbit interaction, not saying that we need a particular dv, v of r only. Okay. So here we only need the following thing. We need a potential energy landscape that is position dependent, therefore you have a gradient. Okay. The second form equivalent is that I don't like to write it as the spin angular momentum. I like to write it as the Pauli matrix. That's fine. Off by h bar over 2. So this 2 becomes 4. And that is the popular form in solid state physics. Okay. So you will see sigma dot into grad v cross p. And even worse, when three vectors have this form, A dot B cross C, they are equivalent cyclic forms. And one form you often see is the following. It is sigma cross grad V dot into P. Okay? Now, these two forms are very popular in condensed matter physics nowadays. For the reason that it emphasizes, all in all, you need a potential energy function that is positional depending, okay? And then you can take a gradient on it. If it's very flat, no fun, okay? No gradient, no slope, okay? You need that. And it also emphasized that the electron is moving in it. So momentum, that is the electron's momentum, okay? So it emphasized that it has to do with the electron's motion in a potential energy landscape and moving in a clever way. For example, moving perpendicular to the gradient, then you will have very good grad V cross P, okay? You move along the gradient radially, outward, no fun. You can't get anything. You have to, you know, you see the cross product. It is so this formula tells you more in a pictorial way, okay? So these are popular forms, alternative forms in other fields for spin-orbit interaction. Again, if you don't like all this, take this final page, summary page with you, and you can go into atomic physics laboratory, do your topological material research, whatever, okay? So I would like to take equation 16, again, let the formula speak for itself. This formula emphasizes the magnetic dipole moment is being taught into a B field. The B field is grad V cross P, okay? So again, I write 1, 2, 3, and you should read it as 1, 2, 3 in particular order, okay? So appreciate what the formula tells you. You see a P, it means when the electron moves, okay? Now you see grad V cross P, means when an electron moves perpendicularly to the gradient of a potential energy landscape. By that I mean, you can think about space, and then you have grad V, V everywhere, therefore you have the change. The change will give you something like a roll, a platform that is curving, changing all the time. That is a landscape of V, okay? So when an electron moves perpendicular to a gradient of potential energy landscape, then there will be an effective magnetic field given by this cross product. There's an effective magnetic field that will dot into the electron's spin. Okay? Now that is the conclusion. I hope you to appreciate the conclusion, because we start off with a particular scenario with a nucleus and the electron. Okay? But if you take the end result and stretch your mind a little bit, you can move away from that particular atomic scenario. As I mentioned several times, how about a solid? So a solid, you have many nuclei, each one is contributing something like it's a Coulombic attraction. But when you have an array, the landscape of this potential energy function will be periodic and rather complicated. Nonetheless, there will be gradient, and that will be okay. So even in that case, the electron moving in such situation, if as long as it's not parallel, so it is moving, there is some cross product remaining, there will be a magnetic field that is affecting the electron's own spin. And that's the conclusion. Okay? It's rather fascinating, I would say. Okay, so this is what I try to say. So in a solid, you have this, not so clean. An atom is easier to think. So you have V of R, then you have simplification, go to here. Okay, but in a solid, we usually see this because that is the general thing. We all only need a gradient of V landscape. Okay, so summary, we have derived these general forms, popular forms, and atomic physics in particular. We will make use of this to move on in the next part. But the final remark is that we will also have spin-orbit interaction even in the nucleus. Okay? Now, a nucleus is composed of proton, neutron. Both proton neutrons are fermions, spin half. Okay? And even we don't think about the electrons, just inside the nucleus, we again have a quantum mechanics problem. Okay? Can we think about it something like this? We focus on one proton, and all the other nucleons, so-called neutron and protons, you know they are strong force, right? Nuclear force, or nuclear force, different from Coulomb, okay? So all the other nucleons are exerting the nuclear force on one proton that we are focusing on. So basically, we hope that we can think about it as one proton moving in a potential energy landscape due to all the other nucleons. And proton is spin half, so it has a spin magnetic dipole moment. So therefore, the whole game is the same. It moves in this landscape. It has orbital angular momentum. But since we have a gradient V, it also generates a spin-orbit interaction term. And in fact, we need that to explain something called magic numbers observed in nuclear physics. You might have heard of it in 1122, the earlier physics course. Okay, it is about that when a nucleus has some particular numbers of protons and neutrons, for example, 20, okay? Then this particular nucleus is stable. It's more stable than if it has one more neutron or one less neutron or one more proton or one less proton. These are called magic number, okay? For example, now in recent months, a very hot topic in nuclear physics is that the experimentalists are trying to study double magic number nucleus, meaning the proton metric number, the proton number belongs to one metric number, the neutron number also a metric number, will that be particularly ultra stable? Okay, so there are works like that. And in order to explain this metric number, it turns out that spin-orbit interaction, but now not electrons, but protons and neutrons, is a crucial component in the theory. And that theory won the Nobel Prizes, I think 1960 something, okay? So what we discussed today, although our discussion is particular for start with an atom, actually it can be applied in many different scenarios. So I would like to motivate for a few minutes what's next, and then we will do the details next time. Very naturally, we would like to understand the consequence. So what? We just derived this term, big trunk, but F a function of R, S dot L. Last term, you solved this Coulomb only part for hydrogen atom. You are very happy, you get all these states. 1s, 2s, 2p, okay? And even including spin, up, down spin, fine. You get all this, and then you know the energy. We also study that we can relabel these states using GMT. But it's just relabeling. If we have the same basic Hamiltonian, the energy will be E and L, meaning 2s, 2p, things like that. Okay, in general for central force Hamiltonians. So the question becomes, we derived a spin-orbit interaction term. The Hamiltonian becomes a new one called H. So it's a classic scenario. H equals H0 plus H prime. How can we handle this extra term? At least approximately. Okay? Can we do first order perturbation to get something out of it? The answer turns out to be yes, if we are clever. Okay? So that's the question we will try to answer next time. The big picture is we have S dot L. Okay, so we have this. Now, we know two different labeling schemes. We can label the states by the old way or by JMJ. Now we have a choice. Will this new way be better than the old way? Right? The new way has the label of total angular momentum and L and S for L vector and S vector. But there's no mention about the Z component anymore. We replace it by the total and the total's Z component. So the whole thing next time is 30 seconds, okay? Very simple. We have L dot S. What to do? L dot S is by vector sign, it is J squared minus L squared minus S squared divided by 2, right? You just square this. You have J squared equal L squared plus S squared plus 2 L dot S. So you can express this in terms of J squared. Bravo, done. So if you use this new scheme, you will not be afraid of J squared, L squared, S squared, because J squared is just small j, J times J plus 1, H bar squared, done. This is L times L plus 1, this is half times half plus 1, H bar squared. Everything is done, okay? So in using the new scheme, suddenly this spin-orbit interaction term can be treated easily within first order perturbation theory. And we find why there will be fine structure, and that's the story. But the calculations still need to be done. Okay, so that is the big picture. And now I hope that you can tie things up. Why we first introduce how to add things, because we need the J here. Second, why we need to introduce how to relabel things in terms of J, because we want to handle this term this way. Okay, and we will develop this next time, next Tuesday, before the Chinese New Year. Okay, so see you next time. I will stay around for some questions.